morning, guys. Welcome to the class of CE331, Environmental Engineering 1. So we're discussing from the last class the filtration, right, and the mechanisms that is involved in filtration. So we saw the majority there are four steps, right? The mechanical straining.
স্যার একটু জোরে বলবেন স্যার।
We discussed that there are four major steps: mechanical straining, flocculation, and sedimentation and adsorption. And then we'll start from here today. Biological metabolism. What is biological metabolism? You see, this is the filter media. You have the filter media here, right? Now, when the water percolates through this filter media, this water is wastewater, so it does have organic matter in it. It does have organic matter in it. Organic matter. Organic matter. These are the waste, right? Now, you have bacteria here, right? In this water, you also have bacteria. Bacteria. Here, you also have bacteria. Microorganisms, actually. So, what happens is that these bacteria eat this organic matter because organic matter is a food to these microorganisms. So they eat them, they break them down, they take them as a food. So what happens that organic matter plus bacteria, right? Bacteria, in, they actually oxidize them. They actually oxidize them. That means oxygen. Now, all organic matter is basically what? The complex bond of carbon hydrogen. Am I right? Am I right?
Yes, sir.
ইয়েস
Yes,
স্যার।
sir.
Bacteria, in the presence of oxygen or sometimes in the absence of oxygen, oxidize it and produces carbon dioxide plus water plus other products. Plus what? New bacteria or new cell. Cell. That means these bacteria eat the food, break them down, take energy, and produces more bacteria. Produces more. Therefore, you will see there is a grow of bacteria all through the surface of the media. This is a bacterial layer. This is a bacterial layer. Are you following me, guys?
Yes, sir.
Yes, sir.
Yes, sir.
And, and this layer is gelatinous. That means it's sticky. So what happens when new bacteria comes in from the waste? When new bacteria comes in from the wastewater, like this water is coming, it has bacteria. Since this is gelatinous, this layer is gelatinous, this layer is gelatinous, they actually adsorb new bacteria. They adsorb new bacteria cells. Also, if you have smaller particles here, these also gets adsorbed here. That means they are being removed. So that's another process or mechanism how filtration removes colloidal particles from the water. Is it clear? Is it clear?
Yes, sir.
Yes, sir.
And then finally, electrolytic action. The electrical charge on the sand filter and the ionized matter in water reacts to alter the chemical constituents of filtered water. Sometimes you have um, compounds which is positively charged or negatively charged. Therefore, when you have ions, when you have a pollutant in water which is negative or positive charge, then they react or gets attracted and are being removed. So that's also another process, electrolytic action. So these are mainly the four um, mechanisms how filtration um, removes pollutants from water: mechanical straining, flocculation, biological metabolism, and electrolytic action. Okay.
So can you please repeat the fourth one?
Electrolytic action, right?
Yes, sir.
So let's see what they're telling. They're telling electrical charges on the sand filter. That means sometimes you have ions adsorbed here, and therefore this surface of the filter media might be charged positively or negatively. And when you have a pollutant, positive or negatively charged, they are attracted here and are being removed. That's what I said. That's it.
Okay,
Clear?
sir.
Now, this figure actually represents whatever I had told you. First of all, flocculation, coagulation, and these things happens. And did you see biological slime? What is biological slime? This is the
Gelatin.
the layer of the bacteria. This is the biological slime, which is sticky and which can absorb bacteria. So this is biological slime. What happens? Adsorption or interception. This is also kind of, I mean, getting attached with the surface. So you should be able to describe filtration, the mechanisms involved in filtration with the neat sketch. Okay. So biological layer. Sometimes it's also possible instead of biological layer, you also can form a chemical layer which is also sticky. When you add aluminum sulfate in water, aluminum sulfate usually you'll find it with attached molecules of water. Okay, so when you add it, you'll get aluminum hydroxide, and this aluminum hydroxide will create the same types of layer, which is gelatinous. Okay, and that will exactly works the same way as bacterial layer will work. This is also gelatinous, and this will also absorb the bacteria and other micropollutants and colloids. The chemical layer can also be formed. So that's what they're telling, that adhesion of bacteria on gelatinous coating from geological film. Geological film, that means bacteriological film. Bacterial film. Okay, zooglial film means bacterial film around the sand grain in which biological activities are carried out. Detain bacteria, that means captures bacteria and remove organic matter in slow sand filter. You know what? There are different types of filter media. As I discussed previously, you have slow sand filter where the water passes slowly, that is slow sand filter. There are another types of filter where the water passes rapidly, that's a rapid sand filter. Are you following me?
Yes, sir.
Now, this bacteria takes some time to form, right? So these bacteria take some time to form. Therefore, therefore, in rapid sand filter, it's difficult to form the bacteria. In slow sand filter, you can form the bacteria because the water is moving slowly, so you can form the bacteria, and bacteria gets enough time to form. And in case of rapid sand filter, what you can do in that case, because bacterial film is unlikely to form, therefore, in rapid sand filter, you use chemical. That means here, instead of making bacterial film, you form the chemical film, the chemical layer, the aluminum hydroxide. Is it clear?
Yes, sir.
So in slow sand filter, you have biological layer, and in rapid sand filter, you have chemical layer. Now, this figure shows the general features of the slow sand filtration. So basically, here is the slow sand filter. Here is another slow sand filter. That means they are using two slow sand filters series, in series, one by one. First of all, the water will move from here, slow sand filter 1, and for further treatment, the water will move to the next slow sand filter, slow sand filter 2. And this types of arrangement is what? Series, right? Series connection. So this is series. Are you following me?
Yes, sir.
Yes, sir. Yes, sir.
Now, before this slow, before the water enters in the slow sand filter, you need to make arrangement for pre-treatment. Pre-treatment. That means You need to clean the water to some extent before you put it in the Slossen filter. Okay. Now this is the roughing filter. RF means roughing filter. Okay. If we go back there, we have what? Slow sand filter, rapid, rapid sand filter, and coarse media roughing filter. Okay. So this is basically a roughing filter. What is U? U means upflow. In a filter, in a filter, this is the filter medium. These are the filter media. Now, the water can move from there to there, or the water can move from there to there. So this is downflow and this is upflow. Am I right?
Yes, sir.
Yes, sir.
So URF means upflow roughing filter. Upflow roughing filter. Okay. And why you are not directly giving it into the slow sand filter? Because in slow sand filter, um, before putting it into directly into the filter, we are making some pre-treatment so that um, this filter does not um, get clogged, does not get clogged very soon, does not get clogged very soon. That means if the water is too polluted, if the water is too polluted, then you'll have a lot of particulate matter all together, and they will eventually block. They will deposit. They will be deposited in the filter media, and eventually will block these pore spaces. And if this blocks the pore spaces, then water will not flow from here. Okay, so that's why we are reducing the pollutant load to some extent by applying a flow roughing filter before it goes to slow sand filter. Is it clear?
Yes, sir.
Yes, sir.
And this can be a flow roughing filter, or it can be a plain settling tank or sedimentation tank. Settling tank is the sedimentation tank, same thing. Settling means sedimentation. Remember, we discussed sedimentation tank in detail. Hmm?
Yes, sir.
This is
Yes, sir.
sedimentation tank. So you may also pre-treat the water in sedimentation tank. Now, even after doing this, and this, your water may have your water may have some bacteria. Okay, and this bacteria and this bacteria can harm our health, right?
Yes, sir.
Even a single bacteria can also harm our health. So what you can do is, finally, before collecting the water, we use chlorination, chlorinator. What chlorinated or chlorination? So why do you add chlorine? Because chlorine kills the chlorine, CHLO. Alright, so chlorine kills the pathogen. Chlorine kills the pathogens. Okay, and so killing the pathogen, that is called disinfection, which is basically disinfection. So therefore, we perform disinfection here. Okay, and then we collect the water. Separate it. So just before collecting the water, we apply the process of disinfection by applying chlorine or any other suitable media to kill the pathogens. Clear?
Yes, sir.
So that's it. So it was slow sand filter. Now this is a rapid sand filter. In rapid sand filter, you are also using two rapid sand filters in series. This is a particular condition. You may not always use two. You may have to use three, four, or five. Okay? Or one. It depends. Are you following me?
Yes, sir.
The figure is showing two. That doesn't necessarily mean you have to use always two in series. You may use one or more than one. Any number. And before the rapid sand filter process, again you need to pre-treat the water by sedimentation, and before sedimentation you apply coagulation and flocculation by using alum dose. What is alum? Aluminium sulfate and water. Aluminium sulfate connected with water molecules. Is it clear? Fitkiri basically. Clear. And
Yes, sir.
similarly, to the previous case, before collecting the water, we are applying chlorination or disinfection. Clear? Is it clear?
Yes,
Yes?
sir.
Okay.
Yes, sir.
In slow, look at here. What is this? Wash out. What is wash out? There are two output. Did you see? One here is the clean water they are collecting, and the another is wash out. Wash out means the debris and any other um, sedimented particles, pollutants. They can wash out. Here also you have a wash out arrangement. Wash out. Okay.
Yes, sir.
So now, what is backwash? Again, wash out. What is backwash, by the way? You know what? If you had a filter media here, so you have filter media here. So as I said, you have the pollutants here, right? Pollutants here. So these pollutants accumulates with time. These pollutants accumulates here. Okay. So the open space or the porous space or the pores in the interstices of the particles gets narrower. Therefore, the water can pass through them easily. So therefore, you have to wash the filter media regularly after a certain interval. It can be 1 month, 2 months, 3 months. Are you following me?
Yes,
You have
sir.
to
Yes.
wash. You have
Yes,
to
sir.
wash out the filter media because this filter media will be clogged out eventually with time by the deposition or settlement of the particles or pollutants. What you can do, you can bring them up this gravels or filter media and wash them thoroughly and put them back. Okay.
Yes, sir.
but remember but remember, when you wash them, the bacterial layer will also be destroyed, right? The bacterial layer will also be destroyed, am I right?
Yes, sir. The gelatinous layer.
Yes, sir.
Gelatin. So what will happen that you need to give some time for this media to have the biological film grown up on their surface. Once you replace them, you need to give them some time, some days, and that is called maturation period. That is called what? Maturation period. That means the formation of the bacterial layer. Maturation period. Is it clear? Hmm?
Yes, sir.
Okay, now what I was talking about, another way of maintenance of filter media, that is, you have the solid particles deposited here, right? So what you can do is, normally your water, for example, your water is moving from this direction to this direction. This is the exit. Now what you can do, uh, you can stop adding water from here for the time being. You stop adding water from here. Okay. And instead of doing that, you start adding water from there by pressure or any other means. You reverse the direction. Clear?
Yes, sir.
Yes, sir.
And then what would happen that these pollutant particles, these pollutants which were deposited here, they will go up. They will go up, and you can easily collect them. right?
Yes, sir.
Yes, sir.
With this water, they can be collected. On the other hand, if you have the flow of water in this direction, then you can stop it and reverse the direction from. By the way, if your direction of water is here, then the pollutants are gonna have here, right? Majority of the pollutants will be here. So what you can do, you can reverse the direction of the water here, and what would happen? Due to the force of this water, these pollutants will go out with this water, and you can collect the water. Is it clear?
স্যার ম্যাচুরেশন পিরিয়ডটা স্যার আরেকবার একটু বুঝুন স্যার।
The same thing. This is the opposite of this, nothing else. This is just the opposite of this, nothing else. Same thing. Clear? Did you understand this one?
স্যার
Yeah, then this is the opposite, nothing else. Okay?
ওকে স্যার।
So what you are doing in this case, you are reversing the direction of water. You are reversing the direction of water. So this is called backwash. That's why it's called backwash. Clear, guys?
Yes, sir.
Here are the characteristics of these three types of filter media: the slow sand filter, upflow roughing filter, upflow roughing filter, this slow sand filter, this upflow roughing filter, and rapid sand filter. Rate of filtration, as you can see that this is 0.2 to 0.4 meter per hour. What does that mean? That means in 1 hour, the water passes how much? The water travels a distance of how much? 0.2 to 0.4 meter. Is it clear, guys? Is it clear?
Yes,
Yes,
sir.
sir.
The velocity of water. Here the velocity of water is 0.2 to 0.4 meter per hour in slow sand filter. But in rapid sand filter, this is what? 5 to 10 meter per hour. This is quite understandable because this is rapid. Water will move faster, and this is slow. Water will move slower. Is it clear?
Yes, sir.
Yes, sir.
And slow sand filter forms what? Biological film, and that biological film takes some time to form. That's why ripening, that's called ripening time, formation of the biological film, and that is 0.25 day to 30 days, up to 30 days. But in rapid sand filter, this is chemical, right? We use chemical, right? Huh?
Yes, sir.
So how much time does it take to form the chemical layer? Only 5 to 10 minutes, because this is chemical, and that's why this is faster. And in upflow roughing filter, this is kind of intermediate. Clear? Oh, not intermediate. This is, I mean, yeah, this is faster, this is slower, and this is something I mean, it's kind of larger than slow sand filter. Okay. Particle size D10. D10 is the you know the 10% finer. Okay, effective size of the particle. Oh, which particle? Which particle? This particle. Filter media, basically. Filter media. Here, this is zero point 0.1 to zero point 0.3 millimeter. This is 0.45 to 0.55 millimeter. And this is 5 to 8 millimeter. So this is very large particles. Are you following me, guys?
Yes,
Yes,
sir.
sir. Yes, sir.
Suitability. In slow sand filter, this is suitable for water which has a turbidity less than 50 NTU. But if your water has higher turbidity, in other words, if you want to remove or if you want to treat a water which has higher turbidity, like greater than 50 NTU, then you will have to use rapid sand filter. And if it's 50 to 150, again you can use upflow roughing filter. But if your NTU is less than, if your turbidity is less than 50 NTU, you can use slow sand filter. Clear, guys?
Clear, sir.
Pre-treatment. Slow sand filter requires pre-treatment. Rapid sand filter requires pre-treatment. But upflow roughing filter does not require pre-treatment. Sometimes you may use upflow or downflow roughing filter. Okay. Under drainage system washing process. Under drainage system, let's look at a filter media. Okay, this is a filter media. We have cut it down. We have cut it down to show you clearly what's happening inside of it. First of all, this is some trays. Did you can you see there are some trays?
Yes, sir.
So water is gonna pass through there and fall from here, and these are the filter sand. So water will percolate through this filter sand. And then again you have different types of filter media. This is gravel, right? So gravel. So as the water percolates through this filter media, it gets treated and you get cleaner water. And finally, here, finally from here, you collect the clean water using perforated laterals. Perforated means which is porous. You have pore. Okay. Now look at this. First of all, look at the arrangement of the size of the particles. At the water is moving from here, from top to the bottom, right? And at the top, you have put the finer, the smaller particles. And as you go down, you have increased the size of the particle. Did you see this? Smaller, smaller particle, smaller, a bit higher, and even higher. Are you following me?
Yes,
Yes,
sir.
sir. Yes, sir. Yes, sir.
Okay. So the reason is why this is happening. Why did you arrange like this? You have a smaller uh, sand particles here. That's fine. Now, if you don't have any larger particle here, then what would happen? These smaller particles will come out with the water and go and enter into the perforated lateral pipes. And in the water, you will get sand. Do you want that?
No, sir.
No,
So
sir.
that's why you are capturing the larger particles, sorry, smaller particles with larger particles. So now these particles will be resting upon them, right? And then again larger particles. So these particles will now be captured by the even larger particles. And finally, as the water moves, you'll get clean water, and these smaller sands will not be able to come here. You'll get clean water. Is it clear? That's why
Yes, sir.
Yes, sir.
arrange the gravels from smaller to larger size. Okay. Now operation difficulties. When you run a filter, there are some difficulties, some problem arising, like mud accumulation. You know, here you have mud, right? So this is the filter media. So here, since you have pollutants and particulate matter, they will accumulate at the pore spaces of the filter media, and that's why you have to clean them regularly, as I told you. Mud accumulation, cracking of filter, and jetting. You know, if I draw it again, so look at here. If the water passes from there, it will get friction from this particle and from this particle. Am I right?
Yes, sir.
But if the water percolates from here, it will get friction from this particle and from the side of the filter media. But this filter media is smooth or easy because this is straight. Am I right?
Yes, sir.
So therefore, the velocity will be higher here. And since the velocity is higher here and velocity is lower here, there will be more force acting upon this. And since there is a force difference here and there, tell me if this is particle, this is larger force and this is smaller force. What would happen? Where the particle will go? In this direction, right?
Yes, sir.
So at a time, you'll see this the particles at the periphery of the media, they are moving towards, they are shifting basically here, okay? And therefore, you'll see a gap here. You'll see a gap, and that's a problem. So they are referring to this cracking a filter and jetting, okay? And negative head and air binding. What is negative head? This is mainly because of the um, if you have the filters media here and you have particles deposited in the filter media, pollutants, okay, then what would happen that it will be difficult for the water to pass through, am I right? because they are deposited particles all way around. Are you following me?
Yes, sir.
Yes, sir. Yes, sir.
So there will be friction. There will be friction, and if the friction is so high that the water loses all of its energy to overcome this friction, then finally the water will not be able to move further. It will stop here, and you'll see there is a vacuum. There is a vacuum because the water cannot pass through. The water cannot pass through. Why? Because all the energy of the water has been exhausted by the higher extreme friction offered by the deposited material over here. Are you following me?
Yes, sir.
Yes,
Yes,
sir.
sir.
If there is a vacuum, and vacuum means negative head, okay, and air binding. So this is, there will be air over here. Vacuum means negative pressure basically, and you'll see that air is trapping over here. So that's a problem. So these are basically the operation difficulties of intermediate. Clear? Any
Yes.
question?
Yes, sir.
Yes, sir.
Now disinfection. As I told you, what is disinfection? Disinfection is
Killing pathogens.
killing pathogen. That's it. Disinfection. Disinfection is killing the pathogens. So disinfection of water is the killing of a disease-causing microorganism, and disease-causing microorganisms are pathogens. Not all kinds of pathogens, by the all kinds of microorganisms. There are also beneficial microorganisms which are beneficial to our health, our body. We are not um, killing them. We are killing the disease-causing microorganisms, and that's pathogen, right? So while sterilization, now if you destroy or kill all types of microorganisms, that is called sterilization. Is the total destruction and removal of all microorganisms, which includes bad or harmful microorganisms and beneficial microorganisms. That is sterilization. We don't need that. We need the disinfection, which is killing only the pathogens. Okay. So, and there are a multitude of processes how we can do that. First of all, natural process. Most pathogens are accustomed to live in the temperature and conditions found in the bodies of humans and animals. In other words, in the warm blooded animals. That means most of the pathogens like to survive in the body of the warm blooded animal. Who are warm blooded animal? We, the human beings, cow, dog. Are you following me?
Yes, sir.
Yes, sir.
Now, if you bring them out of the body of the warm blooded animal, they will not survive, they will die. Like in, I mean, die eventually. Eventually, they will die. Not immediately, maybe, but eventually they will die because their most favorable condition, environmental condition, is available in the warm blooded animal's body. Okay, that they do not survive well outside the body. Storing water for extended period in open tanks or reservoir prior to treatment can accomplish some destruction of pathogens through sedimentation and natural die-off of the organism. More than 50% of the pathogen in water will die within 2 days, and 90% will die by the end of week. That means if you can store the water for certain amount of days, you can achieve the disinfection 50% almost within 2 days and 90% within 7 days or 1 week. But remember, still you may have 10 to 20% of pathogens which might be deadly, which can kill person. So you have to be very careful. Natural die off is not enough for us. Okay. Conventional treatment. Are you following me, guys?
Yes, sir.
Yes, sir.
Sir.
Conventional treatment. Significant pathogens removal also occurs during the conventional treatment process, like when we do coagulation, flocculation, sedimentation, and filtration. We saw that we remove some amount of bacteria, right? In filtration, we saw. Am I right?
Yes, sir.
Even in coagulation, flocculation, we have a flock. We have a flock which is formed by the aggregation of a smaller particle, and this is sometimes gelatinous, and bacteria gets absorbed in this and thus uh, been removed. And they're telling that uh, typical bacterial and viral reduction in coagulation flocculation process are 60 to 70%. Okay, and addition of filtration process can increase the removal close to 99%. Okay. So conventional treatment, that's one thing. Coagulation process, and one thing. Softening process, that is, you can, bacteria like to live in a pH value which is um, in generally 6.5 to 8.5. Okay. Now, if you reduce the pH, I mean, if you um, reduce the pH below this 6.5 or increase it beyond 8.5, then you can achieve some amount of disinfection and destruction by chemicals. This is widely used. We use widely this process, and mainly we use chlorine, and we will discuss it in detail. Or you can use ozone or a strong oxidizing agent like potassium permanganate or chlorine, other chlorine compounds. Okay. Now, addition of chlorine, that's called chlorination. Addition of chlorine, that's called chlorination. So that's a part of disinfection actually. The chlorination of public water supplies and polluted waters serves primarily to destroy or deactivate disease-producing microorganisms. Deactivate or destroy or to kill the disease-producing microorganisms, which we call pathogens. Okay? But when you use chlorine, you need to be careful about one thing. That is, um, when you use chlorine, that can produce trihalomethane in water. which is harmful for our health. Okay, so you have to apply chlorine dose in such a way so that these trihalomethanes are not formed. Your disinfection is achieved. At the same time, trihalomethane is not formed. You have to make sure that. Okay. Now, what is the theory behind the disinfection using chlorine? Disinfection capabilities of chlorine depends on its chemical form in water, which in turn is dependent on pH, temperature, organic content of water, and other water quality factors. Chlorine is used in the form of free chlorine or as hypochlorites. Hypochlorite. Hypochlorite means what? OCl. Hypochlorite. If you add it sodium, so sodium hypochlorite, calcium hypochlorite, Cl minus. Okay. Chlorine applied to water either as free chlorine or hypochlorite initially undergoes hydrolysis to form free chlorine consisting of aqueous molecular chlorine, hypochlorous acid, and hypochlorous ion. What happens? When you add chlorine to water, it forms chloride ion and hypochlorous acid. This is hypochlorous acid. Hypochlorous acid. Are you following me, guys?
Yes, sir.
Yes.
Yes.
So this hypochlorite acid, since this is acid, it gives hydrogen ion and hypochlorite ion. This is hypochlorite ion. This hypochlorite ion. So basically, this HOCl, hypochlorous acid, and hypochlorite ion, which is formed basically by the addition of chlorine to the water. What we got? We got hypochlorous acid and we got hypochlorite ion. These two are the main agents who kill the pathogens, who have the disinfection capabilities. That's what they're telling here. The two chemical species found by chlorine in water, who are the hypochlorous acid and hypochlorite ion, are commonly referred to as free or available chlorine. So these two are referred as free or available chlorine, and which acts as disinfectant. They act as they act as disinfectant. Is it clear?
Yes, sir.
And they are termed as free or available chlorine. Now, if you add chlorine into the water, then which species you will get? Either it is hypochlorous acid, or it is hypochlorite ion, or chlorine itself. It depends on the pH of the water. It depends on the pH of the water. This figure shows that in this figure you have pH in x direction and you have the species concentration in the y, not concentration, percentage of chlorine species. Okay, that's also a type of concentration. Now, if your pH range is 0 to 1, for example, then who dominates? chlorine. Majority of them are chlorine. What is the HOCl percentage? Only this 15, and this is what, around 95 or 90. Is it clear? 200, 200. Is it clear?
Yes, sir.
When your pH is around 2, then your chlorine concentration and HOCl concentration is similar. From pH 3.5 something to 6.3 in this range, who is dominating? Tell me. Who, which one has the highest
Sir,
concentration?
HOCl.
HCl, and chlorine is almost chlorine is almost zero here. And if you increase the pH to 8.5 or something else, then who will be dominating?
Hypochlorite ion.
Hypochlorite.
Hypochlorite ion. Okay, so remember this figure. Now, reactions of chlorine with impurities in water. You know, you are your water is entering into the treatment system, and you are adding chlorine here, and your objective is to kill the pathogens, right? But if your water has organic pollutants in this, organic pollutants in this, and any other pollutants, not only organic pollutants, then this chlorine, some portion of this chlorine reacts with the pollutants to form different species. That means the chlorine which you added to kill the pathogens, some part of them are now being used by the organic pollutants to react with them instead of killing the pathogens. That means you are losing your chlorine. Am I right?
Yes, sir.
Okay. So reactions of chlorine with impurities in water. So these impurities can be organic pollutants or any other types of pollutants. Reaction with ammonia. In sanitary wastewater, ammonia is a very common pollutant. Ammonia. Our body discharges nitrogen containing organic matter which is decomposed to give you ammonia. Okay, so ammonia is a very common pollutants in the sanitary wastewater. Now the free chlorine. Who are free chlorine? Remember,
Yes, sir.
free chlorine. HCl and OCl minus. That means hypochlorous acid and hypochlorite ion. So free chlorine reacts readily with ammonia and certain nitrogenous compounds to form what are collectively known as combined chlorine. So we are telling that this chlorine, instead of killing the pathogens, some part of it is used to react with the organic pollutants or any other types of impurities like ammonia. So this ammonia reacts with the HCl, that is free chlorine, to give you, look at this, one H is gone out, NH2, NH2. and one chlorine from here comes out. So NH2Cl. How many chlorine is there, guys? How many chlorine is there?
One.
One. So that is called monochloramine. Mono means what? One, right?
One. Yes, sir.
It's called monochloramine. Okay. So this NH2Cl now here, this again reacts with hypochlorous acid. Now again one hydrogen is replaced with chlorine and hydrogen becomes one and chlorine becomes two. Are you following me?
Yes, sir.
How many chlorine is there, guys?
2.
Two. So this is called dichloramine. Clear? So monochloramine, dichloramine. Clear? Is it clear?
Yes, sir.
And this happens in pH range 4.5 to 8. This also happens in 4.5 to 8. Now this dichloramine again reacts with HOCl to give you, now the only hydrogen is even replaced by the chlorine and you get, how many chlorine is there, guys?
3.
3. So this is trichloramine. So this is called trichloramine. And it happens less when the pH is less than 4.5. Now, in addition to chlorinating the ammonia, this is called chlorination of ammonia. Chlorine also reacts to oxidize ammonia to chlorine-free products like ammonia can react with the chlorine in the water to give you nitrogen and the other products, or nitrate and other products. Clear?
Yes, sir.
Okay. So, so as you can see that instead this HCl, these HCl were supposed to kill the pathogens, but now they are reacting with the pollutants. So we are wasting. We are getting some HCl wasted. Now the presence and the concentration of these combined forms depends on a number of factors, including the ratio of chlorine to ammonia nitrogen, chlorine dose, temperature, pH, and alkalinity. Okay.
Yes, sir.
Reaction with other impurities. So we saw the reaction with certain types of impurities here, but there can be reaction with other types of impurities also. Okay. Okay, so there can be other types of impurities which can react with the chlorine. And these other types of impurities can be iron, manganese, nitrogen dioxide, hydrogen sulfide, etc. Is it clear, guys?
Yes, sir.
This part is important. Look, chlorine also reacts with humic substances, which is kind of organic matter present in water to form trihalomethane, which is carcinogens. Like, what is carcinogen? The carcinogen means the compounds which produces cancer.
Yes, sir.
So, according to US EPA, that is United States Environmental Protection Agency, US EPA. Like in Bangladesh, we have Department of Environment to protect the environment. In USA, they have United States, United States Environmental Protection Agency. Okay, so they're giving us a maximum allowable level of trihalomethanes in drinking water, which is 100 microgram per liter. If you cannot have more than 100 microgram per liter of trihalomethane in your drinking water, otherwise you may get cancer if you consume that water containing excess trihalomethane for a long time. Is it clear?
Yes, sir.
So, breakpoint chlorination. From here, so the thing is, first of all, we need to determine how much chlorine we need to add. Am I right? How much chlorine we need to add, right?
Yes, sir.
And different types of water may have different types of uh, pollutant concentration. For example, sample A, sample B, it may have another type of concentration. It may be more polluted, it may be less polluted. So the chlorine dose required in sample B is not same as the chlorine dose required to treat the sample A, right?
Yes, sir.
So we need to work on this. We need to know how to do this. So we will do this using breakpoint chlorination. Okay.
Okay, sir.
So next class we will start that. If you have any questions so far on whatever I have discussed, please tell me. Any questions?
স্যার
Go
স্যার একটা
ahead.
কোশ্চেন ছিল ইয়েতে ওই যে
Go ahead.
ওই ফ্রি ক্লোরিনের রিয়েকশনটাতে যে ফ্রি হাইড্রোজেন আয়ন হচ্ছে প্রডিউস হচ্ছে, তো ওইটা কি স্যার পিএইচটা চেঞ্জ করে না?
কোথায় বলো?
নিচে নিচে একটু নিচে স্যার, হ্যাঁ, এই যে স্যার নীল দাগ দেওয়াটা উপরে,
স্যার আরেকটু উপরে।
এখানে।
স্যার এই যে
Can you read last? জি স্যার, এখানে।
স্যার এই রিয়েকশনটাতে তো এইচ প্লাস প্রডিউস হচ্ছে, তো এটা কি স্যার পিএইচটা চেঞ্জ করে না?
Yeah. So look at the origin of this equation. Let's see. You have added chlorine, right,
ইয়েস স্যার।
into the water, and you got HOCl. Now think, where is this H coming from, guys?
স্যার
Did you
ওয়াটার।
did you add this H?
নো
No, you
স্যার।
added chlorine.
ইয়েস স্যার।
Now H was already in the water. H was already in the water. So you're not adding something extra. So that will not increase the pH, decrease the pH. Is it clear? If you had added something, for example, you have added HOCl or You have added hydrochloric acid in the water, then you are adding hydrogen ion, right? That will give
Yes,
you
sir.
H plus Cl minus. That would have reduced your pH, but here you are not adding extra hydrogen ion. The hydrogen ion that you are looking here, that has basically come from the water molecule. That's why it's not gonna decrease or change the pH. Clear?
Yes, sir.
Any other questions, guys?
No, sir.
No, sir.
Okay, then thank you very much. Have a good one. Stay safe.